Alright, grade 12 chemistry. Today we're talking about Q and K and something called the equilibrium law. This is some math that we're going to apply to our concept of equilibrium. Here's the big ideas that we're going to talk about. That first thing is that K and Q are both determined by the exact same equation. So they have exactly the same way of determining them. K is a constant, but Q does actually change. So K is constant, Q changes. You can think K for constant is one way to think about it. Oh, K does change with temperature. So K is specific to the reaction and to the temperature at which the reaction is. Q will change with concentration, and then we're going to compare K and Q to determine whether reactions are at equilibrium or not. So that's what we're going to do. First, we're going to learn the equilibrium law. We're going to talk about determining an expression for K. Then we'll talk about Q, which is that reaction quotient. And then we're going to use Q and K to determine the position of an equilibrium. So that's what we're interested in doing today. Keep in mind, square brackets means concentration in moles per liter. And let's get started on equilibrium law. So here's the equilibrium law. Equilibrium law is based on the forward and reverse rates of a reaction. Right? We have a forward rate and a reverse rate. We talked about that yesterday with like cars on a highway or water in the shower. And rates of reaction will change with concentration. They'll also change with temperature, but concentration is one of the ways that it will change. And both forward and reverse are affected by concentration. So, if you start with everything as reactants and they start going towards products, you're going to lower the rate of the reactant side of the forward reaction. You're going to increase the rate of the reverse reaction because the concentration on the other side is going up. So both reactants and products affect the rate. And we can use rate law on both sides. Right? Forward rate is going to be K times A to some exponent and B to some exponent. And the reverse rate is going to be C to some exponent and D to some exponent. At equilibrium, the forward rate is the reverse rate, and so we can get the equilibrium law. What we're doing is taking both the K's, the K forward and the K reverse, and setting them equal to each other. Well, the R forward and R reverse, setting them equal to each other, and making one K together a unique K that is explaining the position of both the forward and the reverse reaction. So it's kind of just some substitution is kind of going on here mathematically. And this is the equilibrium law. And by definition, we put the products on top because that's what we're looking at making, so that they're more important, they go on top, and the reactants on the bottom. There's no real reason for this. You could have a K where the reactants are on the top and the products are at the bottom, but everyone has kind of agreed to always have products on top, reactants on the bottom. And please note that the exponents are just the coefficients in front of the reactants and the products. So when we actually do some practice problems, this will make a lot more sense. But that is the definition of K. Specifically, actually, this should have a little C on it because it's the concentration equilibrium. So K is what we call the equilibrium constant. Get this over here. K is what we call the equilibrium constant. It's constant for the same reaction done at the same temperature. So that's particular temperature. The reaction will always have the same K. It's dimensionless quantity as well. So there's no units written for K. K is always just expressed as a number. It's just a number. That's it. So let's actually try an example of this. Here's an example of K in action. Here is our reaction. H2 plus I2 becomes 2HI. So what we want to do is determine an expression for the equilibrium. And we're going to use this expression here. K is products to the power of the products over reactants to the power of the reactants. So looking at that here, I'm going to move my thing here. What we're going to have is, and I'm just going to kind of freehand it, is K, right? The K here, K by concentration, is going to equal, it's going to be the products, the products is HI, right, in square brackets, the concentration of HI, But there's a 2 here, right? There's a 2. There's 2 HIs, and that's going to make a squared. HI squared. Over, right? It's products on top, reactants on the bottom. Now these have just a 1 in front of them, so it's to the power of 1. So over the reactants to the power of 1. So concentration of H2 in moles per liter, and concentration of I2 in moles per liter. So what we have here then is the equilibrium concentrations of each of these after various reactions have happened. Like this one, they started with just H2 and I2, and then they got some HI after. This one, they started with all HI, and they got some of this stuff. This one, they started with a little bit of this and a little bit of that, and then you ended up with this kind of stuff. So we want to verify this equilibrium law. So basically what we want to do is we want to put these numbers of H2, I2, and HI in moles per liter into this expression that we just made and verify that they all come out to the same K value is what we're going to do. So I'm going to pause and I'm going to type all of those in because I don't want you guys sitting here for 5 minutes watching me type those in, and then I'll just do the calculations. So here we go, I've written them all out. In black here is the 0.442, 0.442, 3.119. But remember that our expression is that the HI is on top. The products are on top and they're squared. So here you see that 3.119, which is the HI squared, over 0.442 times 0.442, because that's my H2 and my I2. That's my H2 and I2 down here. The second one here in green, you see that here, 1.560 squared, because the HI has a 2 on it, has a 2, divided by 0.221 and 0.221, 0.221, 0.221. Now this one's got different numbers, but it works the same way. 0.280 squared, because the HI is squared, and 0.035 and 0.045, like that. Now let's verify the rate law. I've got my calculator here. And when you put this into a calculator, you have to be really careful about brackets, especially if you're dividing. When you're dividing by these, you have to divide and then have a bracket for the 0.442 times the 0.442. So 3.119 squared divided by 0.442 times 0.442, I get 49.7. 49.79, so 49.8 for that one. For this one, 1.560 squared divided by 0.221 times 0.221, I get 49.8, 49.8. And for the last one here, I'm actually I'll show you exactly what I'm typing into my calculator here's what I put into my calculator, 0.280 squared. And then I went divided by, and then I opened a bracket, and then I went 0.035 times 0.045, and then I closed the bracket. That way I've got, I made sure that I'm dividing it by both of these together. So 0.280 squared divided by open bracket 0.035 times 0.045, 49.8. Oh, hey, look at that, 49.8. They're all slightly different because of, I don't know, I guess rounding or something like that, experimental accuracy. But yeah, you see that that they all come out to the same number, and that's how KC is supposed to work. And that's the equilibrium law. Now the next piece in determining a coefficient for K is what happens to gas phase and aqueous, or what happens to solid and liquid. So A is the concentration in moles per liter, right? The square brackets means concentration in moles per liter, but there are reactions that have liquids and solids. So, the question kind of becomes, what is the concentration in moles per liter of water, of liquid water? It's kind of a weird question. Or what's the concentration in moles per liter of solid silver chloride? How do we define a concentration of a liquid or a concentration of a solid? It's easy enough for an aqueous. It's how many moles of it are in 1 liter of the water. But liquid water is in itself, right? And solid silver chloride is in itself. So it's hard to define. The answer is that they have constant concentrations. Their concentration is a constant. So water is 56 moles of H2O for a liter of water. You can do that from its density. But the point of equilibrium is that, changes to these values will come out to the same number every time. Excuse me. But solid and liquid concentrations don't change. Water is always going to be 56 moles per liter. So because the concentration will change, they don't affect K. And K is unitless. It doesn't matter what unit we put it in. Right? There's no moles per liter or anything that I put here. It's just 49.8. So what happens is we fold the constant concentrations into the value of K rather than having them in that square bracket area. And what that means, practically speaking, is that we set the concentrations of solids and pure liquids to 1 because the units don't matter, and so they just become folded into the K value rather than us having to write 56 every time we have liquid water. We just get rid of it. It's just 1 because multiplying by 1 and dividing by 1 it doesn't change your expression, and because constant concentrations don't change the expression, it makes sense to just set them equal to 1. So now I've got some examples of that happening. This is a normal, it's aqueous, 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 and aqueous. So you get a typical K expression. FeCl2, there's a 2 in front of it, so that's where you get the square, right? There's the 2 here gives us the squared value here. That 2 gives us the square here. Products on top because products are more important than reactants. And SnCl4 just has a 1 in front of it, so it's there. This one here, FeCl3, has a 2, so it's going to be squared. And SnCl2 just has the 1, so it goes down here. So products over reactants, always products over reactants. But then there's some where you have solids and liquids, like here, calcium carbonate decomposing to CO2 and calcium oxide. This is a solid, constant concentration. This is a solid, constant concentration. So the only thing that has a changing concentration is this gas, this CO2 gas, which is a product. And so just the value here is just the concentration of CO2. Technically, it's the concentration of CO2 over 1, right? Because we set this equal to 1. That's like CO2 times 1 over 1 times 1 over 1. So this would be 1 and that would be 1. But because we don't write 1s, we just ignore it. Here's another example where we have copper and silver and copper, but this one's aqueous and this one's aqueous. Here we see that the solid silver is not part of our equation, and the solid copper isn't on the bottom of our equation. That's a 1 and a 1 up there. And then there's a 2 here for the silver, and that squares the silver, squares the concentration of the silver in our equilibrium law. Here we have liquid water that just goes away. So the 2 products are aqueous, and so they stick around on top. And underneath we have the acetic acid, but it's the only thing underneath because this water is liquid, so we ignore it. This one here, gas, aqueous and aqueous. Gases do count. We can find a moles per liter of a gas, and different pressures will have different moles per liter. So the gas does get included. Even though they're different states, even though they're different phases, it's still included in the calculation because it still contributes to equilibrium. So product on top and the 2 reactants underneath. Remember, these are unitless quantities. Technically, there's moles per liter, moles per liter, moles per liter. So this should have liters per mole as its unit, and this should have moles per liter as its unit, but we don't write a unit for K. This is one of those times where you don't have to write a unit in science class. And here, H2O liquid to H2O gas, liquid water turning into gas phase water. It has an equilibrium constant, but it's literally just the concentration of the gas and nothing else. So yeah, that's determining the equilibrium constant. Okay. There's some questions in your book that you could do. This one's showing a reaction 4NH3 plus 7O2 to 4NO2 plus 6H2O. And the question is just creating the law. So here K is going to be the products, NO2 to the 4 comes from that 4 in front of it, H2O to the 6, because there's 6. Now this H2O is gas phase, and gas phase does have a concentration. You know, different pressures have different concentrations, so that one does get added to the equation. Divided by the reactants, NH3 to the 4, because there's 4 of them, and O2 to the 7, because there's 7 of them. So that would be how you do it. And this one here is asking to calculate the position of K, the constant of K for this reaction, and you get the equilibrium concentrations of nitrogen, hydrogen, and ammonia. And this is the reaction here. So let's actually write the reaction. We have N2, 3H2, and 2NH3. K is going to be the concentration of NH3. Products first, concentration of NH3, right, to its coefficient, to the 2, divided by, now the products, the two products, we have just N2 just by itself because there's no number in front of it, just N2, and H2, but H2 has a 3 in front of it, right? H2 has a 3 in front of it, so it's to the power of 3. And we need to actually figure out this expression, like what it's actually going to be. And so we just substitute these values in. So these are in scientific notation. So please, use your calculator. Use lots of brackets to put the scientific notation in. It is going to be 2.00 times 10 to the minus 4 squared over, and remember to open brackets at that point because you're dividing by two things, over the nitrogen, 1.5 times 10 to the minus 5 times 10 to the minus 5, and 3.45 times 10 to the negative 1, and that's going to be cubed, right? That one's going to be cubed because H2 is cubed, and that's my concentration of H2. And then you put that through a calculator, and let me put that through my calculator. 2 times 10 to the negative 4, and I'm going to square that and divide that by 1.5 times 10 to the negative 5 times 3.45 times 10 to the negative 1 cubed. Lots and lots of brackets in there. And I get 0.065 as an answer. 0.065. You could actually do it, step by step, actually square this, actually cube that, and then do everything step by step together. That might be better for you, but you should get 0.065 as an answer. So try this out with your calculator. If you get something different, let me know, and I could help you, how to put it into your calculator correctly. So that's determining expression for K and calculating that expression using K. Next up, we're going to talk about Q, the reaction quotient. So I'm going to pause, and I'm going to get that set up. So now we're going to talk about Q, which is called the reaction quotient. And the thing to keep in mind here is that Q and K have exactly the same mathematical derivation. So Q is going to be done, calculated exactly the same way we did K. So like here we calculated a K value. You do the Q value in exactly the same sense. And what that is, what that means is we're basically just taking wherever the substances are right now, wherever those species are, whatever concentrations they have right now, and throwing them into our equilibrium equation, because it's the same mathematically. And it's a snapshot. It's like, here's where they are right now. They're right now. And that's called the reaction quotient, and that's Q. Q for quotient. Quotient is just a fancy way of saying the final answer from a division, right? So they're the reaction quotient. Same, calculated exactly the same way as K. And at equilibrium, then Q will be equal to K. Q will be equal to K. And the reason that that's important is that if we compare Q and K, we'll know whether we have too many products or too many reactants. Too many products or too many reactants. That helps us tell whether we are too high or too low. I'm going to just copy this here so that we have it as a reference. All right, bring this down, and we'll put that in there. All right, so there's K, and Q would be exactly the same, right? All I have to do is take this K, and I'll just erase that. All right, we'll take that and we'll turn it into just make it white, and we'll put a Q there instead. Right, it's exactly the same. We'll make it a bit bigger. There we go. So it's the same. It's calculated exactly the same way. It is products over reactants. Right? So it's products over reactants. Products over reactants. Right? Products, reactants. Which means that if Q is higher than K, this fraction is big. It's a big fraction. It's bigger than this fraction, than the fraction it should be, which means it's either too much stuff up here or too little stuff down here. But anyway, the balance is too far on the product side. If you have too many products, the reaction will shift towards the reactants, right? It's going to make more reactants, right? It'll shift towards the reactants, and that's shifting left, right? To the left. To the left. If you have too many, if Q is less than K, you have too many reactants, because that means if Q is small, you don't have enough products. The top is too small or the bottom is too big on our fraction, right? For the Q fraction to get to K. So same concept, right? The reaction will shift towards the products, right? You have too many reactants, which means not enough products. Your reaction is going to shift to make more products, which is to the right. And that's how we can use Q and K to predict whether we are on one side or the other side of the true equilibrium, and whether we are going to go left or right. So we'll just do a practice problem here, comparing Q and K. All right, comparing Q and K is our next thing. All right, Q and K. Here's a question from the textbook. If K is 0.0601 for this reaction at that particular temperature, they give us some specific moles per liter, some specific concentrations, and we have to figure out what Q is, and compare it to K, and it'll tell us whether we are too far on the product side or too far on the reactant side. So first off, let's actually make our Q. Let's make our expression for Q. Right here, Q is going to be, when we look up here in our reaction, products over reactants. Products on top, they're more important. Products over reactants. 2NH3. So that's going to be the concentration of NH3 3. There's 2 of them, so it's squared over the concentration of N2, that's our reactant, N2, and the concentration of H2 cubed. H2 cubed. So that's going to be Q for all of these because Q is just determined the same way as K. And then we can put in our numbers, right? 1.00 times 10 to the negative 3. That's my NH3, that's on top. 1.00 times 10 to the negative 3. I'm going to pause while I write the rest of this in. You guys don't need to watch that. Okay, so I've put those in. Remember the squares, that's squared because of the 2 squared, and the cubed because of the cubed. Make sure you've got the right ones. The 2.00 is my cubed one because that's the H2. Put it through my calculator. 1 times 10 to the negative 3 squared divided by, open a bracket because I want to divide by both of them underneath, times 10 to the negative 5 times 1 times 10, 2 times 10 to the negative 2 times 10 to the negative 3 cubed. And I get 125,000. I get equals, for the first one here, Q is equal to 125,000. Not even 125,000, it's like 12 million. It's 12,500,000. That's a lot. It's a big Q, right? Big Q. So Q is very, very big. K, where it should be, is 0.06. That means too many products. Too many products, reaction will shift, because products is on top. We got too much of the NH3 or too little of the N2 and the H2. So we're going to shift towards the N2 and the H2. We're going to shift left. Okay. Same thing for this one here. We're going to calculate it. For this one, we're going to change colors here, maybe in blue. Right? It's the same equation. So now it's going to be 2 times to the negative 4, and so on and so forth. I'll pause and get that written out so that you guys don't have to watch me write. So here we are. I've written it out in blue. My NH3 on top, N2 just by itself, negative 5, and the H2, 3.54 times 10 to the 1, 10 to the negative 1, cubed, because that's in there, it's cubed. So let's put that into our calculator. 2 times 10 to the negative 4 squared divided by, open a bracket, 1.5 times 10 to the negative 5 times 3.54 times 10 to the negative 1 cubed. I get 0. This one, in this case, we'll make it blue so that it matches. Q is equal to 0.0601. Q is 601. Q is equal to K, so reaction is at equilibrium. Right? It won't move left or right. The reaction is equilibrium. The forward rate and the reverse rate are the same speed. And this last one you can probably imagine is going to be the other way, but let's actually prove it. We're going to write that out. We're going to use that same expression. We're going to write that out. So again, I'm going to pause so you don't have to watch me write. So I've written it out. There's my NH3. Make sure it's squared because that's what appeared, squared. 5 for my N2 and my H2, 1.0 times to the negative 2, and I'm cubing that. Let's work out our Q. 1 times 10 to the negative 4, we're squaring that, dividing it by, I'm going to open a bracket, 5 times 1 times 10 to the negative 2 cubed. It's this one gives me a Q of Q is equal to 0.002. Alright, Q is 0.002. Now K should be 0.06. I get 0.002. Q here is less than K. So there's too many reactants, right, or too few products. So reaction will shift to products, and that's to the right. So that's how you use Q and K, and you can figure out if you have too many of one or too many of the other, and which way the reaction is going to shift. Yeah, that's it. We practiced Q and K, we determined their expressions, and we used them to make some predictions about a chemical reaction. Yeah, that's all. We'll do some practice problems in class, and I'll see you there. Thanks a lot.